So, okay, so chapter 3 is one of those chapters that people forget about. They forget about, like, when they get into biochemistry, and they forget about it when they move into being medical doctors and in graduate school and other places. But it's a very, very important chapter, mainly because it's going to change the way you think about molecules. Okay, so that's pretty significant, actually, because up to now we draw molecules on the board, however we draw them, and they are very static, right? And you draw them, and there they are. And maybe you draw them in 3 dimensions, and maybe you don't draw them in 3 dimensions, but that's it. Well, turns out that unless you're at absolute zero, which is really hard to get to, molecules are moving all the time. Not only are they spinning and jumping around in the room, but they're vibrating, so that the carbon and the hydrogens are vibrating back and forth. Okay, and let's see if I can figure this thing out. So this is in your sapling set. So I don't have you buy these kits anymore. But if you want to try to get one of these kits, it might help you a lot. Like if you could just borrow one from somebody else, or if you want to, like I'll have one of these in the lab and you can just go in there and use it. Or if you want to go on Amazon and just buy one. It's, if you're kind of that person that likes to touch molecules and those sorts of things. But this molecular modeler here, and I did get it to work. Page was not found. You can build, I think I can just build this. And then, so here is, so if I rotate this around, you can see how this looks like this, okay? So it's probably a lot easier if you do this with the kits. So we're going to do this with the kits. At least kind of getting some smaller, some groups of a few people, and you could probably help share those kits there, help share these kits over here, and you guys over here, and build that molecule, build ethane. Okay? Build a couple of them. Build as many ethanes as your kit will allow. Okay? I'll build ethane up here. This kit has seen better days. Get that to work. What's that? Yeah, you can go white as hydrogen. So my kid has seen better days up here. I think I'm going to get it to work. Oh, there's those. All right, so do we have methane built there? I've almost got methane built here.
Do you want to build
Ethane. Okay, so I should have built my ethane before I got here. All right. Oh, I'm so close. All right, does everybody have methane built? There are no lone pairs. Ah, I got it. There are no lone pairs. Everybody get an ethane? Hold up your ethane.
Oh, you have a big.
I have a bigger one, yeah. That was a bond cleavage there. Okay, so if you put it in this form, if you put ethane in this form, I'm going to switch this. I'm going to make kind of look down the middle of it. You can put it to where all of the hydrogens are as far away from each other as possible, right? That's one structure. Okay. Let me see if I can do this on the screen. Rotate bond. No, doesn't like that. Oh, it's just gonna. Okay, so I did a little calculation there, and it said the angle between. So if I calculated the angle between, it's called a torsion angle because it's between four atoms, but the angle between two of these hydrogens that are opposite of each other, that looks like 60 degrees. Okay. I should have played with this a little bit more. There's a way in which you can make that bond angle 0. Okay? So let's make that bond angle 0 on your thing. Make this bond angle 0. How would you make that bond angle 0? You don't have to take your molecule apart at all. You're still building one. How do you make this bond angle 0? Just rotate it 60 degrees. Okay? Now that bond angle is 0. The torsion angle is 0 because these are lined up with each other. Okay? Turns out that that's two different energy levels of ethane. Okay? So I could take and I could draw a energy diagram, okay, versus increasing energy. And these two hydrogens are going to be, they're pretty close to each other now versus right there. So that's a higher energy. Just that movement puts it into a higher energy. Oop, I don't need that guy. Just kick him right across the room. So here's the 60 degree one, and at a higher energy is the 0 degree bond angle or torsion angle. Okay, and that happens really, 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 really fast. So if we were to draw what we would say the minimum energy conformation of ethane, you would draw it like this, and we call this staggered conformation. We call this the staggered conformation. So these hydrogens are staggered from each other. Okay? And we call this one the eclipsed. The eclipsed conformation. Okay? Where those hydrogens are eclipsed to each other. Okay? And that happens all the time. All right, so this hydrogen can be anywhere, so if this is my bond angle here, basically I can just keep drawing this to where that hydrogen, those hydrogens, just continue to rotate. See if I drop any more atoms off of this thing. So they just continue to rotate like this, okay? And that would, if it were there, would be eclipsed, okay? And staggered, and eclipsed and staggered. And everywhere in between, this is always rotating. Especially at room temperature, this is always rotating, okay? You get down to, maybe 1 Kelvin, and this rotation may stop, okay? But certainly not at room temperature. So, and it can be anywhere in between. It's just that when it comes up to being exactly eclipsed, that's a high energy, so it doesn't stay. Its time, the time in which it spends at this higher energy is just less than the time that it spends at the lower energy. Doesn't mean it doesn't happen. It just means it's not there very long. Okay, so it's more like a movie than a snapshot. So a snapshot would say, I'm going to take a look at the minimum energy of ethane, and you're going to look at it and you're going to go, oop, there it is. That's what ethane looks like, the minimum energy. Okay, and that's what computer programs give you and all that. But if you looked at a movie of it, you would see, we got a molecular movie here, you would see that sometimes these two hydrogens are eclipsed from each other, with each other. Okay? So, I'll tell you a little story. I was at a seminar, and someone I knew was giving a talk, and he had an enzyme that he was trying to inhibit, and he had these drugs that were to inhibit this enzyme. And they had done molecular modeling like this, more sophisticated, and it showed that these drugs should have this type of interaction. But when he actually did the experiment, it was all mixed up, that he didn't have any correlation between what the computer said and what he found in the lab. And so his conclusion was, I must be doing the experiment wrong. And I've got to go back and redo the results. And so I talked to him later, and I said, actually, your bench experiments are probably exactly right. It's just that when you did your molecular modeling, you didn't give any room for a molecule to have a different shape than its lowest conformation, because molecular models give you the lowest conformation. You put it in there, you say go, it's going to give you the lowest conformation. And so if it's always in the lowest conformation, the way in which that molecule shape then may not fit into an enzyme, may not fit into a receptor. But if you just rotate it just slightly, where'd my molecule go? Let me come over here. There it is. But, so, oh man. Is this all on tape? I have to erase that later. I'll edit that out. So if the computer program says, oh, that's the way in which the shape of the molecule is, to fit into an enzyme or a protein, but if it just moved it just a little bit, and of course there's these are more complex molecules, then the shape might fit better. Well, the energy between that and that is very little. And the binding energy of a molecule to a larger molecule can make up for whatever energy that it costs to maybe move that over just a little bit. So it's the idea that you're thinking about molecules being dynamic, okay, versus static. And typically, we've always talked about molecules being static, but they're always moving in some way. They're always dynamic, okay? Any questions there? I think I'm going to kill this because I'm not sure I can. Let's see what happens if I keep building molecules. So if I do, okay, so yeah, okay, so let's do butane. So we just did ethane. Let's do butane. So here's butane, and if you look down, so go ahead and build butane. I'm not going to build butane on my little model kit here. But let's see if I can get butane. Oh, I want it. You got butane up there yet? Okay. I'm going to need more boards, so I'm going to kill this now. 4 carbons.
Good.
4 carbons. And 10 hydrogens, right? Okay, so you got butane? All right, I'm going to kill this because I'm going to draw it on the board. What's that?
Did you rotate them all?
Butane? You got butane? Okay, I'm going to kill this now. Okay, so you got butane there. Things are just flying everywhere today. All right, so this was ethane. So just CH3, CH3. So let's do butane. Just CH3, CH2, CH2, CH3. Okay? So you got a butane there? Okay. So what I want you to do is I'm going to draw it like this. And I want you to put it in this conformation. I'll do this one too. Okay, so what I've done there is I've said that everything that is a wedge is coming forward that's in this part of the room, and everything that is a dash is going into computer science. Okay, so right, like if you hold this up just like this, I'm going to move that bond just slightly right there. So he's got this just like I've drawn it there. So well, sort of, kind of. There we go. Now we have it just like I've drawn it there. So we got this hydrogen on this side is up, and it is in the plane of the board. And I'm going to rotate that one. And that hydrogen is down, and that's in the plane of the board. And then you've got these hydrogens that are coming forward and going back. Does everybody see that? Okay. Now, I want you to take that, and I want you to look down the 2-3 bond. So switch, and so see how you're looking down the 2-3 bond now? So look down the 2-3 bond. This is 1, 2, 3, 4. So look down, put your eye, well, you know, you can put your eye over here. This is a really bad eye, but put your eye over there, or you can move the molecule, okay? But look down the 2-3 bond. And what does that look like? If I look down the 2-3 bond, what does it look like? Where are those methyl groups going? So I'm going to draw it like this. I'm going to say, it doesn't matter which way you do this, but I'm going to say that the front carbon is this dot. So this is carbon number 2, is the dot. And the carbon number 3, the back carbon, is this circle. Okay? So if I do that, I have this methyl group on the back carbon coming down, and I have a hydrogen and a hydrogen going up. And then on this one, I have a CH3 going up and a hydrogen coming down. Okay? Does everybody see that? Can everybody imagine that? So look down, go ahead and get your molecule and see if you can see that. So if you need to share molecules here. Did everybody see, if you just kind of say that the back hydrogen is the circle and the front hydrogen is the dot, that you can do that. Oh, I messed up. What you guys let me mess up like this for? There we go. Okay, so everybody see that? Now, I want you to just rotate these hydrogens rotate as well, but we're not going to worry about those so much. What I want you to do is I want you to rotate the front carbon just slightly. So we're going to keep the back carbon the same. Okay? But I want you to rotate the front carbon. Let's say we're going to rotate it clockwise. Just rotate that. Does it rotate easy with your molecules? Just rotate it, and this methyl group will come, right over the top. Everybody put that in the same of a hydrogen. It comes right over the top of a hydrogen. Okay? So here, let me. There you go. Perfect. So what rotation did we have there? What degree angle do you think that is? Well, we got to go all the way around. It's 60 degrees, right? So that's a 60-degree rotation. So from there to there is 60 degrees. Okay? And then let's rotate that another 60 degrees. And so I'm going to leave you put that there. So that's another 60 degrees. Oh, my arrow got off here. Okay. Did everybody get that one? So if I called this staggered, what would you call that? Would you call that staggered? I mean, they're all staggered from each other, right? Yeah. And then if I called this one eclipsed, would you call that one eclipsed? Yes, that's eclipsed as well. And so what would this one be? That's staggered again. So let's do another one, 60 degrees. So the best way to do this is to pick one. Either pick the dot or the circle and don't move it. Okay, so I picked not to move the circle. And I have to draw that kind of long because I got to get it out here. Okay? And then I'm going to draw this again. I'm going to do it again. We're going to leave that the same, and then we're going to put the methyl group here. Okay? And then I can do it one more time. And I'm going to leave this the same. Okay? So if I go one more time, I'm back to this one. Everybody get that? If I go one more time, I'm back to that. All right, see if you can do that. Just look down the 2-3 bond with your molecule and just move it. Can you do that? And that's just that's just the rotation of butane around the 2-3 bond. Okay? Everybody see that? Have I lost anyone yet? You're all there? Okay, so then let's think about this in an energy form, okay? In an energy diagram, which of those structures, so there's 6 of them, which of those structures puts the 2 methyl groups the farthest away from each other? I saw a hand motion. So which one do you think? We'll number this. We'll number it. A, B, that's his joke. C, D, E, and F. Okay, we'll letter it. All right, which one do you think? A? Okay, so A should be the lowest energy. So I'm going to just write it down here, okay? Now, which one should be the highest energy?
D.
Because you have those 2 methyl groups that are like eclipsing each other, right? Mm-hmm. They're right on top of each other. So that's going to be the highest energy. So here we got B in here, C in here, and we're going to say D is way up here. Okay? So, and then let's judge the energy difference between A and B and C. And let's see if we can get to D. So what do you think? B is going to be higher energy, but which is going to be a lower or higher energy, B or C? You think B is lower energy? What's your rationale?
They're 120 degrees apart instead of 60 degrees apart.
Get your confirmation in B.
So B would be right here. And there's 120 degrees.
No, that's not B. B, your B is right here.
That's where I just have it.
I don't think so. But look at here. What's happening here? What's happening there? So everybody get their confirmation into B. Would you call B a staggered confirmation or an eclipse confirmation? See how that's eclipsed? So what do you think? B or C?
Lower or higher? What's the question?
Is if we were to judge the difference between B and C, which one would have lower energy? I think C has lower energy because it's staggered, right? Not eclipsed? Okay. So I'm going to put, and then if we said that, so I'm going to put C here, and I'm going to put B over here. Okay. D is higher, so then let's go to, what do you think, what about E? E is going to be lower than D, but is E, do you think E would have the same energy as any other of the structures on there?
C.
You think E and C would have the same?
Yeah.
They're basically, if you just flip the molecule over, it's the same, right? So yeah, so that should be the same. A, B, C, D, E. And then F, what do you think? Do you think F has the same energy as anything else on there?
B.
You think B?
Yes.
Okay. Does that look about right? So if we were to draw an energy diagram of this, we would say, you know, if you move it all the way around, ooh, I just barely caught it there. And then it would come back down to A, right? That's my next structure. And that is the energy diagram for butane. Yes?
Are there supposed to be two B's?
I have two E's.
Two B's, you have two B's.
Oh, E,
This one of those was going to have.
F. Oh, because it's the same as B.
Oh, okay.
That's why but yeah, it's F. I said F probably. Okay, so, all right, so that's the energy diagram. That's the way in which the relative energy would work between how you would, around the rotation of that 2-3 bond, okay? So, all of the lower energy ones, A, C, E, A again, are all staggered. Okay? They're all staggered. All of the higher energy ones, B, D, and F, are all eclipsed. Okay? Doesn't mean that you don't get there. Oh, I think my battery's going to run out at some point, but doesn't mean you can't get to D, because really to get to, say, from A to E, it has to go through either F or D, one way or the other. It has to get there. Okay. So we have some names for these types of structures too. No one's confused on that. Everybody's got that. We're all good. Wow, I did such a great job. So. So we have some names that we put on these. We call this one anti, because the two largest groups are completely 180 degrees from each other. Okay? And we call this one gauche. I think I spelled it right. Did I spell it right? E at the end?
It's A.
Oh, okay. There we go. Gauche. Gauche. Sounds like some good designer jeans or something. So, gauche?
Sounds French.
Yeah, probably. We could look up the root where that comes from. But so here, this one is gauche as well. Okay? What's that?
Yes, C-N-E-R.
Well, you get gauche because of the relationship between these two methyl groups. So these are only for the staggered. So they're only for the staggered conformations. And here, those two methyl groups are, they're not anti, and they're gauche. We say they're gauche to each other. That's how we're gonna. That's the
It's French.
French.
It's for left.
Left.
Yes. That's what it is. Cause
Well, it went right on that one though.
I don't know. That's just what it is.
We'll have to.
You can look it up, but I'm pretty sure that's how you spell it in French.
Okay. Well, Google could probably help us. So C and E we're going to call gauche, and A is anti. Okay? Anybody find my cap anywhere? Okay.
Oh, I stole it from you.
Almost found it. Okay. So that seems pretty straightforward, right? And the concept is that, if you were to freeze this out, the lowest energy is going to be A, but at room temperature, you're going to populate some amount of B, some amount of C, D, and E. Going back to my example with with the person that was given that seminar is that the computer is always going to give you this number. It's always going to give you the very lowest energy number. But there are other energy minimums that can be populated that are higher in energy, but they're not like horrible in energy. Okay, they're not high enough to where you will never achieve them. Okay, so then if we were to label this graph, we would say that A here, this part of A, is the global minimum. It's the global minimum, and D is the global max. Okay? And then we would say C and D are local minimums, and B and A are local maximums. Okay? And so you have, you could have a molecule that, let's say that let's say the binding energy between A and C, so if it's in the conformation of A, or if it's in the conformation of C, let's say the binding energy to a enzyme or protein is 10,000 times greater, right? Well, that's enough energy easily to have it have that conformation of C when it does its binding. But the computer, it's not smart enough yet. It tells you just A. Okay? So, kind of get the concept about that? All right, so we're gonna do one more. You're gonna do one more. So get out a piece of paper. You got a piece of paper? And we're going to do 2-methyl butane. Okay? 2-methyl butane. So see if you can do this. See if you can write some. If you've read ahead, what kind of structures are these? Newman structures. These are called Newman structures. Newman projections. Yeah. Newman structures or Newman projections. Okay, so if I say write the Newman projections for 2-methyl butane, that's what you're going to do on an exam. But it won't be 2-methyl butane, it'll be something else.
You always want 2 in carbons 2 and 3?
I can ask the question. So the question is, do you always do carbons 2 and 3? I can ask the question anyway, right? So I could ask 1, 2, and then you would just have an ethyl group hanging off the back carbon. But that's kind of boring right now because they're all hydrogens at the front. Or I could ask, I could have a pentane, and I could say carbons 3 and 4. Or, but yeah. What do we think? I can do it actually pretty easy on the board because it's an erasable marker here, so. So if I did that right. I think so.